Here's number 13 from the Larsen 8.9 worksheet. Check the focus here. And what we want to do is deal with this function g of x equals 3x over x squared plus x minus 2. And we're looking to get these expressions in this type of form so we can maybe use a geometric series. We have a binomial here, but from our experience with partial fraction decomposition, we know we can break this up into two fractions. It will probably look more like this. So we can factor this, x plus 2 times x minus 1. And then we can go ahead and rewrite this as 3x over x plus 2 times x minus 1 equals a over x plus 2 plus b over x minus 1, which is our partial fraction technique. And integration by parts, we use that also, but partial fraction decomposition here. And we want our center to be 0, so we don't have to do too much work after this. So we get a common denominator, so we multiply this by x minus 1, this by x plus 2. And if these fractions are equal and the denominators are the same, the numerators are the same, so we have this equality. A times x minus 1 plus b times x plus 2 equals 3x. Okay? And then we try to find out what a and b are by eliminating one or the other by picking a right value of x. So if I pick x to be 1, 1 minus 1 is 0, so the a term vanishes, and I have 1 plus 2 is 3, b equals 3, so b equals 1. If I have x equal negative 2, the b term will vanish, and I've got negative 2, and negative 1 is negative 3a. And if I put negative 2 in here, 3 times negative 2 is negative 6. So divide by negative 3 and a equals 2, so those are my values of a and b that will yield the same fraction if I added those. So I've got 2x plus 2 over 1x over x minus 1. X plus 2. And you can see now we're more like what we want. So we'll just kind of use the commutative property to reverse these, maintaining the sign in front. So I've got 2 plus x, negative 1 plus x, and it's beginning to look more like this. This is very much like this, so I need to have a 1 here. So I divide all the three terms by 1. I'm sorry, by 2. 2 divided by 2, 2 divided by 2, x divided by 2. And make this a double negative to make that a positive, and then I have this in this form, a over 1 minus r, and my r is going to be negative x over 2 in this case. Here I just need to make this a positive 1, so I divide by negative 1, negative 1, negative 1. I've got negative 1 over 1 minus x, and my a is negative 1, and my r is x. So there we go. And then this is just going to be the geometric series. It's going to be a, which is 1, times r. This is r to the n. And this is just this is going to be a negative 1 times r to the n, and that r is x, so just x to the n. And we're all set. So g of x will equal the sum of these two series. And what I did was I took out the negative 1/2 to the n, wrote it as a separate factor. So I've got negative 1/2 to the n times x to the n. And then I've got over here negative x to the n. And then we could factor out the x to the n if we want, and then we have this. So if we're going to take derivatives, it would, or antiderivatives, it would be easy to work just with this and keep this coefficient stable. Now, how do we figure out the interval convergence? Well, remember, if we're adding two series, the interval convergence is the intersection of the two intervals of convergence. So for this series, my r was negative x over 2, so the absolute value of that has got to be between negative 1 and 1, or the absolute value of this has got to be less than 1, but the absolute value of this will be just x over 2, and then that means absolute value of x over 2 is going to be between negative 1 and 1. Multiply by 2, and this is what we have. And this is already set. X is between negative 1 and 1, so those are my two intervals of convergence, and they intersect at negative 1 and 1. In other words, this is the smallest set that are in both. The intersection would be the smallest that they have in common. So negative 1 and 1. Okay? So if that makes sense, a little bit more challenging problem.